Okay, I started recording. You can present.
Yes. Okay. So, hello everyone. Today we are going to present our randomized course project, and we chose the paper online algorithms for the Santa Claus problem because we thought it was a fun online algorithm, and we wanted to see what we could contribute to that. So the problem statement is essentially we have this set of items and we have a set of children, or we can call them agents, and each item is valued by the children differently. So let's say there are like say five children, child 1 2 3 4 5, and then there's this item one which child one wants it with like say point 0.5, child one values it with point 0.5 value, child two values it with point 0.2, and so on. And then so there are like multiple items. Now the problem itself is we get the items one by one, and we need to assign these items to one child. Like as we get the items, we need to assign the items to one child, and once we are done assigning one item, we get the next item in. And our goal is to make sure that all the children are as happy as they can be, as in the child who's the least happy, this should be maximized. So more formally, we can say that there are a set of m presents to be distributed among n children, and each child has some arbitrary valuation. So it's basically maximizing the minimum valuation any child gets as we distribute the presents. So offline, this is for an offline case. This has a very like this has a straightforward solution. There's no ambiguity in the solution as such, and we just have to kind of see which allotment maximizes the minimum valuation for each child. But since the presents are arriving online and we don't know anything about the future presents, that's where the main challenge lies. So in practical terms, this is kind of very significant. For one thing, online advertising is where this helps a lot. Say I have a website with me and I want to give my ad space to a bunch of bidders. So I don't know how much the bidders value my ad space, and I also don't know if I'll be getting the bidders again. But at the same time, I want to say maintain relations with each of the bidders. I don't want any of them to feel that they're not getting any ad time at all. So in this case, I would need to ensure that all the bidders get say somewhat a bit of ad space, a bit of advertising time. So here, that's one use case of this online Santa Claus problem. Another more practical application would be organ donation, where once again we have a set of patients waiting for different organs, and the different valuations here in organ donations come in via that say different blood groups or different compatibility of the organs themselves. So there's a bunch of patients waiting for an organ, and then we have an organ donator. So we I don't know in the future whether I'll have more people who are going to donate organs. All I know is the valuation of the people, and I want to save as many lives as possible. So the aim is to kind of maximize the number of lives saved, and as a result, as a result, I would need to kind of use this uh, online allotment of organs. So that's kind of the practical significance of this. So the paper we covered uh, came up with a very good came up with pretty good bounds on the uh, lo- they came up with pretty good bounds. So they obtained three very key contributions. So the first one is if the if it's a fully adversarial setting, so the adversary can control both whatever items we get as well as the order in which the items we get, or as well as the order in which the items arrive. Then there is no online algorithm that can obtain a competitive ratio of better than 1 by n. So this is kind of proved with a very simple example as given in the paper itself. So let's say these are our three agents, agent 1, 2, and 3, and we have an input schema of this sort. So in our first input is like say equally preferred by the all three agents. All three agents value our first input as 1, but whereas for every other input, the third agent has no valuation. The third agent doesn't care about the remaining inputs. So in this case, only if we say allot the first input to the last agent. So when they're like say n equal to three agents, only when we allow the first input to the last agent, that's the only way there's a non-zero valuation of the minimum valuation the agents get, and any other allotment simply gives you a kind of zero valuation to the third agent, and as a result the minimum is a zero value. And so the paper basically argues that, so let's say there are n agents, and we have like the first item which is arriving is a kind of public item which all agents value equally, and then every other item which arrives is not valued at all by one particular agent. Let's say the first agent doesn't value any of the other items. So kind of in this case, only if we allot the first item to that first agent, only then the value of the minimum changes, and in any other case the value of the minimum remains zero. So and then for any online algorithm, since it does not at the right at the start, it has no idea which agent is a public agent or private agent. Like all agents are equivalent with probability kind of 1 by n. The algorithm on expectation, the algorithm allots the first item to the first agent 1 by n times, so the competitive ratio is 1 by n. uh, so after that, the paper makes a couple of more important results. So the second, so yeah, and so seeing that fully adversarial setting has a strict lower bound and an upper bound. We do a slight relaxation. We now assume that the items arrive in a random order, and now in this case, the paper provides an algorithm which is useful. So the paper provides an algorithm that has a computed ratio of 1 minus epsilon. But this is under the assumption that the value of the optimal solution, like in the optimal solution, whatever the value we obtain as the minimum, that has to be at least log n by epsilon square. Uh, so in that case, then the paper provides a 1 minus epsilon computative ratio algorithm, and this 1 minus epsilon ratio can also be and even though this is a fractional allotment, if we like if through randomized rounding, which is, let's say, item there's like three agents, and item one is allotted to each of the agents by with like zero point 0.2 of item one is allotted to agent one, 0.4 is allotted to item two, and zero point 0.4 is allotted to item three. So randomized rounding is basically agent one gets the item one with probability 2 by 10, and the other two get the item with probability 4 by 10. So if we do randomized rounding, the paper proves that the integral allocation of items that retains the optimality of the fractional allocation. And finally, the paper also argues that yeah, so this for this the value of the optimal solution had to be at least log n by epsilon square. And the paper also argues that when the uh, when the value of optimal solution is less than ln n by epsilon, there's a epsilon difference in the denominator. Um, then there is no algorithm in the random order input model that has a computative ratio of 1 minus epsilon. Uh, So yeah, this is one bound which the paper has left as an open problem. So when the value of optimal is greater than or equal to log n by epsilon square, then it has a computative ratio of 1 minus epsilon. And it also proved that when the value of optimal solution is less than log n by epsilon, then there is no online algorithm. But we do not know anything about the results when the optimal solution lies between c log n by epsilon and log n by epsilon square. So yeah, so the algorithm provided is a kind of a greedy approach algorithm. So and instead of just trying to like say, it's not a direct greedy algorithm as such, but it's kind of like a smoothed greedy algorithm where they make use of the log sum exponent function. Log sum exponent function is defined as phi of u is equal to minus 1 by epsilon into ln of summation of e to the power epsilon ui. So we at each step we kind of aim to maximize this function considering the previous allocations. And and another thing is, as we allot more and more items, there is more and more dependency within the items created. So to kind of minimize these dependencies, we kind of divide the items into two stages. Like the first m by 2 items, we maximize this log sum exponent function, and then we just restart. We just ignore all these m by 2 items, and now we again maximize the log sum exponent function for the next m by 2 items. So the algorithm proves that on kind of doing this approach, on greedily maximizing the log sum exponent function, we kind of get a 1 minus epsilon competitive algorithm. So yeah, this was like walking through the proofs used in the paper, uh, and that was they chose log sum exponent function in particular because of two main things. There was the concavity property of the log sum exponent function, which was very useful, and we could also prove that the the gradient there was a property related to the gradient that they used in the paper. Uh, and apart from that, there were a couple of interesting open problems which the paper did not resolve, and this could be like future line of work. The first thing is, yeah, like I said before, there's a competitive ratio of 1 minus epsilon under the assumption that optimal is greater than equal to log n by epsilon square. Uh, and there's no online algorithm and optimal is less than log n by epsilon. But then the gap between these both is the unknown area, and that gap can be bridged, and there could be some interesting results. And another result is the fact that there is no 1 minus epsilon competitive algorithm when optimal is less than equal to ln n by epsilon. But there could be some other competitive algorithm. Maybe there's a 1 minus 2 epsilon competitive algorithm, or 1 minus 3 epsilon competitive algorithm. That is something which hasn't been touched upon in the paper, and that's another interesting open problem. So yeah, and we have also done a implementation of the algorithm itself to kind of see how well it does in practice, and Karan will kind of take over and explain our process through that.
Yeah, so now I will be explaining our implementation. Okay, so what we do here is we take the input as a vector of vectors where m represents the number of items that we're getting and n represents the number of agents. And in order to check the average of all of the ways to get the input, uh, in basically to check the average of all permutations that the adversary can give us, we make the array of all permutations that m can have, uh, and then we're essentially running the algorithm for all of these permutations and checking the worst value and the average value of over all of these permutations. Now I'll go on to the implementation of our online algorithm. So, like Dhanush mentioned, it's a greedy algorithm where we split the algorithm into two halves. First, we'll run it for the first half of the items, and then we run it for the second half of the items. As you can see, I have two vectors, one for like the first half of the iteration, one for the second half, and we're starting off from zero in both cases. What we do is we want to maximize the log sum exponent function for each iteration. So here first we'll go to the logsum exponent implementation. This is quite simple and straightforward. So the value of e, we have stored it as 2.71. We could go like further for a more precise answer, but since we're just doing a rough estimate of the we're doing a rough implementation, we decided to stick it to three significant digits. Yeah, so we have a log exponent function where we add the power of each item's valuation to each person. and then we're taking the log of that and dividing it by like the negative of epsilon, and returning it. Apart from this function, we also have an estimated version of the function which adds a little bit of randomness. However, this wasn't performing as well as the log sum exponent itself, so we decided to not include this into our testing. However, I'll just explain what we are doing here. So the value of log sum exponent is guaranteed to lie between the value log n, like the minimum of the entire array, and the minimum of the entire array minus log n by epsilon. And then we're trying to find a random value between like 0 and log n by epsilon, and then subtracting it from the minimum value. Yeah, so this introduces a bit of randomness, but as I said, log sum exponent was doing far better than this implementation. Okay.
And maybe also mention the reason we had to do the estimate in the first place. Like,
Oh, right. Yeah. So essentially, this algorithm is the implementation of the algorithm that we're doing is like very. It has a very high time complexity. So I was trying to reduce the complexity wherever possible. So this estimate actually runs faster than this log sum exponent function, because here we're trying to take the power to some value which runs in a log of this power time. So it's slightly worse than this. This is always a constant time function, whereas this has a log n factor to it. Yeah, so this was the implementation. Now back to the online algorithm. What we're doing to max the log sum exponent function. So differentiating this function is actually kind of painful. So instead of differentiating it, we're trying to kind of come to the neighborhood of the minimum value. So we're not trying to find, uh, wait, sorry, we're trying to find the neighborhood of the maximum value. So we're not trying to find the maximum value of the log sum exponent function, but we're trying to find an approximate distribution for which we end up getting the maximum. So here we have a get all combos function, and what this does is it gives us all possible ways to distribute the number one into n variables, such that each variable is like a multiple of 0.1. So this way we'll have like let's say for n equal to 2 we'll have 0 and 1, 0.1 and 0.9, 0.2 and 0.8, and so on. For n variables we'll have like almost n factorial combinations. So this is why the runtime of the algorithm is not that great, but it runs quite well for small values of n, uh, and it almost always gives us like a good neighborhood for the maximum value of the log sum exponent. So we're running it like we're trying to find the value of log sum exponent for all combinations of this zero point 0.1 uh, distribution that we have, and we're finding the maximum value of the log sum exponent function, and then using that index we're adding those values to the final array, and then we're doing this twice. So first for the first half, and then for the second half. And then we're adding the values, the two values that we've obtained from the two half splits that we've gotten, and then we're returning the minimum value. So this is our online algorithm. Now I'll try running it for a couple of cases. So this one's a pretty simple case where what we're doing is we have 90, 80. 190, and then 90. So this is a pretty simple case. You can just assign 100 to everyone, and then that will pretty much uh, guarantee like the best case. However, it is not guaranteed that we're going to get 100 each time. So you can't essentially say that you're going to give 100 to everyone. You have to be a little smart about it. So the okay, also we're running it using an epsilon value of zero point 0.1, so the ratio should be around zero point 0.9. And as you can see, the average value here is 89, and the average and worst case here are same, because like no matter how you permute these three, it essentially comes out to be the same distribution. So it's fine to have the average and worst case be the same. And since the average value is 89, which is like 0.89 times the best value, which is 100, so it's quite close to the zero point 0.9 bound that the paper got. Now I'll go with one of the test cases that had like the best ratio. um, so I'll just copy that case here. Okay, so we have four items and four agents, and the best distribution here would be give the first person 100, give the second person 90, give the third person 200, and give the fourth person 100. And the answer in this case would be 90, and the 1 minus epsilon approximation in this case would be 81. So the average that we're getting is 84, which is quite above uh, the worst case, the 1 minus epsilon approximation, and even the worst case is quite close to 81. So yeah, this is a case that the algorithm performs really well on. And yeah, that's pretty much it from the implementation side. Thank you.
Right. So yeah, we kind of did a small scale literature survey and included a bit of implementation to test how well the algorithm does in practice. And here we kind of found that the expected value is very close to the 1 minus epsilon ratio that they provided, which was good. But apart from that, even the worst case was doing pretty well. The algorithm was handling the worst case pretty well. Uh, so yeah, in the end, it was a pretty good algorithm to use in practice. The main issue we had was regarding the calculation of log sum exponent itself, the maximization of log sum exponent, which we had to solve taking a
Brute
which we had
force
to solve
approach. Yeah.
approximately using a brute force approach. But apart from that, yeah, this was kind of our implementation and project.
Yeah.
Yeah. And yeah, we've also provided the links to the test cases and the code in our report.
Yeah.
Yeah, so that's pretty much it. Thank you.
Thank you.